Good afternoon, everybody. Let's continue our discussion about telescopes. In this video, we're going to talk about what effects the atmosphere have on telescopes and our ability to see the universe. We're going to talk about two main effects that the atmosphere has. They're going to be broken into two separate videos. Here in this first video, I'm going to talk about how the atmosphere is acting like this turbulent sea of air that is distorting the images as the light comes down from outer space into the medium of our atmosphere, and then reaches us here at the surface of the Earth, or our telescopes here at the surface of the Earth. And for this, I want you to imagine the atmosphere, which extends upward for about 100 kilometers or so. I want you to imagine it as a giant swimming pool, but instead of water, you have all the atmospheric gases, mostly nitrogen and oxygen. But here we are, if we were to dive down to the bottom of a swimming pool, and then look up out of the swimming pool and say that your friends are going to lean over and wave to you from outside the pool. Your friends that are standing outside the pool and the entire world outside of the pool wouldn't look normal. Everything would be sort of wiggling around and being distorted as that light travels through the water and reaches you at the bottom of the pool. We're going to have the same problem with our atmosphere as the light from, say, Jupiter is coming from outer space into our atmosphere. Our atmosphere is not perfectly still, it has turbulence, and the moving air will distort the images, make the images wobble around, just like when you were looking outside of a pool, or if you throw coins into a public water fountain, the coins on the bottom look like they're wiggling about. Jupiter will look like it's wiggling about, so you don't get this nice clean image of Jupiter. You get a distorted image. And depending on how turbulent the atmosphere is, you'll get more distortion. That's this video, is that the atmosphere is like a turbulent sea of air. And the next video, we're going to talk about the rest of the electromagnetic spectrum and how our atmosphere basically absorbs almost all of it other than radio wavelengths. All right, so we have this concept in astronomy that we call astronomical seeing, which we usually just call seeing instead of always saying astronomical seeing. And really what this is it's describing this trying to look out of a pool of our atmosphere effect. Here is a cartoon, an animated GIF of a star. And our atmosphere is not perfectly still. Parts of it are moving, and some parts are moving at different rates than others. There are turbulence in the atmosphere. Some pockets of air are warmer, some pockets of air are cooler. Everything's sort of shifting about. Remember that as light travels from one medium to another, from the medium of outer space, a vacuum, into the medium of our atmosphere, air, then refraction will occur. Light will bend, it will change its path. And each part of the turbulent atmosphere will bend the light a little bit differently, which means that as the light comes from the star through space and enters our atmosphere, it's going to have a wibbly wobbly journey down to the surface of the Earth, where the light's going to get bent around. And since it's constantly moving, the atmosphere is constantly moving, the path that it's going to take to reach the ground, the light is going to always be shifting. So it looked like the image of the star is jittering about. If you were trying to stare at it, it looked like it's moving about. And this, combined with angular resolution, is actually why we see stars twinkle, is this jittering motion. Now, what does this mean? Because the jittering motion, we can't basically see how fast those movements are. We just observe a twinkling or an effective blurring of the images. How does this actually look to our eye or to really a telescope? So here we have all these moving pockets of air, which are now drawn as different pockets right here. Here comes our light from the star, nice parallel rays coming down, nice and controlled. And then it enters our turbulent atmosphere where refraction changes the path that the light takes. So it's not coming in with all these nice parallel rays, which when I was showing you how a reflection off of a curved mirror focuses light, that was our assumption. Here is coming in from all sorts of different angles. So they bounce at slightly different angles when they hit the curved surface of the mirror, meaning that the light doesn't come to a nice clean focus due to the atmosphere causing everything to wibble wobble around. So instead of getting a nice clean image at the diffraction limit of the telescope, so you'd see the star with the size of the diffraction limit of the telescope, instead of seeing that, you see a bigger, blurrier image, where how big and blurry that image is depends on how turbulent and disturbed our atmosphere is. So this is what we refer to as astronomical seeing. It's the term that we use to describe how the atmospheric turbulence are blurring our images. And really what it's doing is going to limit our angular resolution. It's going to make us have pretty blurry images. Here's another example, a sort of a live feed of several images of a crater on the moon, just taken on in a series of images with a pretty turbulent atmosphere. So you can see it looks like everything is wiggling around. No, the surface features of the moon aren't wiggling around. Our atmosphere is, and it's changing how the light is reaching the camera to record this image, making it look like it's wobbling around. It's almost as if you're trying to look at this image through, like somebody's holding up a picture and you're looking from the bottom of a pool out at it. All right, I'm gonna come back to this one right here. And just to repeat, that atmospheric seeing is the word that we use to describe this atmospheric blurring. But we do a little bit more than that. We actually associate atmospheric seeing with a quantity. We quantify how blurry it makes our images. So whenever we talk about seeing, we're going to say how blurred our images are. So it takes a nice sharp image and then it blurs it to what size, what angular size. So if the atmosphere blurs out images, so this dot has a width of say 1 arc second or 2 arc seconds or 3 arc seconds, we would say that we have 1, 2, or 3 arc second seeing. And typical seeing for clear skies at a good observing site is about half to 1 arc second, which means that even in some of the best places on Earth to do observations, the smallest image you can get of any object is half an arc second to 1 arc second, regardless of the diffraction limited angular resolution of the telescope. The atmosphere is blurring up images. And that's a pretty blurry image. That's much bigger than the diffraction limit of even small telescopes. So really what it's doing, since it's making all of our images blurry, is making them look bigger and blurrier, it's a practical limit on our angular resolution. So if we had a pretty good night of like a nice winter night here in Tennessee with super clear skies that are super calm, we might have say 0.8 arc second seeing. Then if we were looking at stars that have a half arc second of angular separation, even if we had a telescope that's powerful enough to see those as 2 distinct points of light, they would get blurred together into a blob. And that's what this is trying to show. So here are 2 stars, a binary star system, which you can clearly see in this that they are 2 stars. And then over a series of about 10 minutes, so these are taken at 2-minute intervals, the atmosphere becomes very, very turbulent. And this captured a time series of basically the seeing going from good, like say half arc second seeing, to bad, say 2 arc second seeing, where you can see them and then you can see them as distinct stars. And then you can see it's getting worse. It's harder to tell, even harder to tell. And by the end, the atmosphere is blurring out the 2 stars, the images of the stars. So it's just one blob of light. If I took that picture, I couldn't tell you if I had 1 star or 2 stars. So it's a practical limit to our angular resolution. Let's actually see how that works in what we call a seeing limited resolution instead of a diffraction limited resolution. So in the last video, I talked about the diffraction limit angular resolution of the James Webb Space Telescope. We imagined we were looking at the star Alpha Centauri with James Webb Space Telescope, which we calculated out the diffraction limited angular resolution. James Webb Space Telescope would see an image of that star that has an angular size of 0.0385 arc seconds. That's the smallest image that that telescope can make. Now let's imagine that we took James Webb Space Telescope. Well, let's just take it where it is. Let's just take it out of the warehouse that is, or the place that is being built right now, and observe with it from the surface of the Earth instead of outer space. where we got to deal with the atmosphere. So let's imagine that we're going to go to some of the best sites in the world for doing astronomical observations, extraordinarily good astronomical seeing of zero point 0.3 arc seconds. So in outer space, this is what James Webb Space Telescope would see Alpha Centauri as, a dot with a width of 0.385 arc seconds. In a Earth-based site that has very good astronomical seeing of zero point 0.3 arc seconds, this is what James Webb Space Telescope would observe, even though it has really good diffraction limited angular resolution. It would see a dot, and yes, I scaled those to the correct size, it would see a dot that has a width of zero point 0.3 arc seconds. We just lost a ton of detail. Seeing is a major problem in astronomy, and we must endure it. We must suffer it living on the surface of the Earth because we can't just get rid of the atmosphere. So how can we get around this? Well, one way to get around this is if the atmosphere is the problem, let's get above as much atmosphere as we possibly can. Let's build our telescopes high up in the atmosphere on the tops of mountains. Let's also find mountains that are known to have locations that have relatively calm, dry skies. So you get above most of the atmosphere can't blur up images as much. You're going to limit the seeing. You go and build telescopes on mountaintops and places where you know you have clear, calm skies, then you're going to limit astronomical seeing, which is why all the world's best telescope facilities are in these remote locations on tops of mountains. No, astronomers are not just afraid of people and hermits that hide out on mountaintops, although yes, some of us are kind of like that. But so are pretty much everybody. We always find some hermits that will hide out. But we don't just build them on mountaintops to get away from people. We build them on mountaintops to limit astronomical seeing, to limit the blurring due to the atmosphere. We also put them on remote mountaintops to get away from city lights because light pollution, light being produced by cities and human activity, is really making our skies bright from a earthly vantage point, which blocks out, makes the sky brighter than a lot of the faint stars, so we can't see them. So we need to get away from the city lights as well. I do have some information about light pollution in the lecture slides, which I always assume that you have read through them before you watch my videos on the same material. Okay, so getting above the atmosphere by building telescopes on a mountaintop is great. Why not just get out of the atmosphere and launch telescopes to outer space? Well, we had to wait for a space-based technology system. We had to become a civilization that can put things in space before we could do that. But now we do that, and we try to do that. The only problem is launching big things into outer space is incredibly difficult. And even when we can accomplish it, it's incredibly expensive. There is a more modern solution as well. Instead of just getting out of the atmosphere or up above as much of the atmosphere as possible, why don't we just use technology, because humans are clever, to work around the atmosphere? If we can detect how the atmosphere is blurring up images, how it's making the light path, the image of the star bounce around, why don't we just correct for that? And yes, we can do this. We build these technological systems called adaptive optics onto telescopes, which are there to cancel out, to correct for atmospheric blurring. And we're getting dang good at atmospheric optics. Adaptive optics. So whenever I say the term adaptive optics, I'm just referring to a technology that we put on telescopes that is going to read how the actual atmosphere is blurring images, and then in real time feed that through a system. So it has to read how it's blurring images, feed that information to a actual mechanical system that will then deform a mirror in the telescope using little tiny pistons called actuators on a mirror to change the shape of the surface of that mirror so that all the light will come to a nice clean focus and cancel out the blurring of the atmosphere. That sounds ridiculous because you have to read out how the atmosphere is changing your images in near real time, then feed that to a system where you physically deform a mirror surface on the nanometer scale in real time. that sounds like sci-fi, except it's not. It's science reality. We actually have these systems. And the point of them is we cancel out the wiggling around due to the atmosphere. And that drastically improves the angular resolution of ground-based telescopes so that they're operating at very close to their diffraction limit. They're almost as good as in space. And we could build really big things here on the ground without all the trouble of trying to launch, say, an 8-meter telescope into outer space, which we still can't do that. How does it actually work? And now I get to talk about this fun image over here. Everything in this image is real except for the words that I added of pew, pew, pew. But yes, this is a yellow laser being shot out of, I believe this is the UPenn telescope, one of the 4 telescopes on the Very Large Telescope, the VLT array. What it does is going to fire a laser that goes up into part of the atmosphere called the ionosphere, where it's looking where we know that we have some atoms up there that will absorb the electrons, those atoms will absorb this wavelength and then re-emit it, thus creating a false star in the sky that this telescope can see. So then that light will, as that light gets re-emitted, the telescope will see that light as it travels all the way through the atmosphere, so it can read out how that light is jiggling around as response to the atmosphere moving the image around. It creates what we call a guide star using a high-powered laser. And yes, you can see that laser with your eyeball shooting into outer space. Then it's going to read out how that guide star is moving around. It's moving this way, that way, this way, that way, this way. Read that out in real time. Feed that through a computational system and a mechanical system that will then deform usually the secondary mirror in real time, so make small adjustments using actuators on the nanometer scale, deform the surface on the nanometer scale to reshape the mirror so that that mirror is now a specialized mirror to cancel out the current state of the atmosphere. And then microseconds later, it has to deform again. Microseconds later, it has to deform again. Microseconds later, it deforms again. And each time it's canceling out, it's reshaping itself to be the perfect mirror for the state of the atmosphere at that very moment. Absolutely absurd, amazing, amazing technology. And it works. It works really, 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 really well. Uh, it removes a lot of the need to send telescopes to space to get great angular resolution to operate near the diffraction limit. So adaptive optics at this level has only been around for about a decade or so, but it works really, really, really well. I just want to show you a animated GIF of how the system works. So here would be a star or a guide star. It comes down through our atmosphere. You can see it's going to make that light all wiggle around. Let's wait for the adaptive optics off. Normally I'd just hit a mirror and that wiggly light would go through and you'd see a star that's wiggling around. You turn on the adaptive optics. So you send off some of that light into a computer system that then sends it to a control system that will deform this mirror, making it the perfect mirror for the atmosphere as it currently is. And then you have a steady star. Let me show you how this actually looks. So here is the Keck telescope, a 10-meter telescope in Hawaii with adaptive optics off. And then they turn the system on. And look at how the detail in the image increases. Notice you can't even see if there are any stars in this region. And then all of a sudden, you can see all of these stars. A huge increase to the angular resolution. And let's use my favorite example before I show you some examples. I really like the VLT telescope. I've been lucky enough to be on a proposal where observations were taken. Unfortunately, I was not controlling the telescope, but I was on the proposal to do observations. I'll show you some slides of that here in a second. But it's made me really like this telescope, and it is the most advanced adaptive optics system in the world on a telescope. With the adaptive optics on this 8-meter telescope, a single one of every one of those telescopes is an 8-meter mirror. The adaptive optics give it an angular resolution, even with turbulent atmospheres, of 0.063 arc seconds. If you remember from the previous video, that's the same angular resolution as the Hubble Space Telescope from the ground. And this is old information. They're much better at this now. And they're getting to the point where they can push it really close to the the diffraction limited angular resolution. So these telescopes operate in the infrared. So at 1 micron, this telescope would have an angular resolution of 0.03 arc seconds, the diffraction limit. And we're getting really, really close to that. So no longer do we have to send telescopes into outer space to get them to operate at their diffraction limit. We can do that from the ground with these adaptive optics systems. Some examples. So here are the 4 biggest moons of Jupiter viewed with the Hubble Space Telescope. Here is Europa. So all 4 of them are Io, Europa, Callisto, and Ganymede, although this is closest, second, farthest away, third farthest away, farthest away. So here's Europa, the best image that Hubble can get of this very, very exciting icy moon that's a little bit smaller than our own moon. Here's an image that the team I was with got of Europa using VLT, that telescope right here. And we can get a much higher quality image. Here is VLT of Neptune. This is with adaptive optics on. We can study the storms on Neptune and see some detail. This is what Neptune looks like with no adaptive optics. And that's what Neptune looks like with the Hubble Space Telescope. So it's outperforming the Hubble Space Telescope. And one last one, because it's not just used for planetary stuff, and I wanted to emphasize that. Here is a star cluster. Same cluster viewed, the star cluster NGC 3603, viewed with Hubble and viewed with the VLT. Notice that you can see more stars with the VLT because it's having better angular resolution than Hubble is. So we can correct for the atmosphere. And it's super cool technology, so I want to share it with you. I will see you in the next video.